Right, so today we're going to talk about chi-square test for goodness of fit, which is really just another hypothesis test where we're going to have a null hypothesis and an alternative hypothesis and check to see whether or not we can reject that null hypothesis. This is all based out of primarily probability experiments where we have these different outcomes that we expect to happen, and we have some expectation on the probabilities. So for instance, I've got a die here today that we're going to be talking about rolling, and we want to see whether or not this die is an actual fair die. This has different outcomes. It could land on 1, 2, 3, 4, 5, or 6. And we have expected probabilities if it's fair. We expect the probability that each side rolls is 1 out of 6. And so if we have some type of outcomes and some expectations on the probabilities, then we can test to see whether or not those probabilities are satisfied. And that brings us to our null hypothesis and our alternative hypothesis. Our null hypothesis is going to be some claim on the probabilities. Sometimes those probabilities will all be equal to each other, like on a die rolling each of the sides, or sometimes those probabilities will be equal to specific numbers. So for instance, you might have the probability of the first outcome is 1 out of 6, but the probability of the second outcome is 3 out of 6, or 1/2. And having those probabilities stated is the most important thing. We expect something with regard to those probabilities, and that's what the null hypothesis is stating. The alternative hypothesis is we're trying to check whether or not those stated probabilities are true. So the alternative hypothesis is that they're not, that there's a difference from those stated probabilities. And that's something that we're actually going to be able to determine using the chi-square test. So the way that the chi-square test works is just like the hypothesis test that we talked about in the past. We're going to get a test statistic. The test statistic for a chi-square test is called chi-square. And what we're going to do is we're going to actually observe. We're going to make some observation where we actually, in this case, we're going to roll a die, but in any situation, you're going to run that experiment, and you're going to have observed frequencies, and you're going to compare that to expected frequencies. So, for instance, if I rolled this die over and over and over again, say I rolled it 30 times. Then what would end up happening is I expect 1/6 of the time it's going to land on a 1. Now that expected frequency for the outcome of landing on a 1 would be 5, because I would expect 1/6 of the 30 rolls would show up as a 1. But if I roll it 30 times, I'm going to see an observed frequency, the actual number of times it rolls on a 1. And so I'm going to compare that to the expected frequency. So the chi-square, what it's going to do is it's going to take each observed frequency, subtract each expected frequency, you'll square it, and then you divide it by the expected frequency, and then we're going to add all of those up. So the reason we do this is because we don't just want to pay attention to whether or not it's rolling a 1, because it's rolling all these different things. We kind of want to pay attention to the entire die to see if it's fair. And so that's how the chi-square is going to work. Now the chi-square, what's interesting is that the chi-square actually fits into a distribution, and that distribution looks a little bit more like this. And what we're trying to see is if chi-square gets big enough, we want to be able to use that idea that that it's not likely to get that big, and so that we can reject the null hypothesis. So we're going to look and see if chi-square gets big enough. If the area under the curve of this, it's not a normal distribution. If the area under the curve is small enough, then we can actually determine whether or not we can reject that null hypothesis. In order to do this, we have to pay attention to a couple of things. One thing is called the degrees of freedom. The degrees of freedom corresponds to the idea that if you're rolling a die, there are 6 different outcomes, whereas if you're flipping a coin, there are only 2 different outcomes. Now, because there are 6 different outcomes, because you might roll more 1s, it's going to take away from rolling 4s or 5s or 6s and so on and so forth. And so you want to kind of keep track of all those things at the same time. We don't know whether or not it's going to reduce the number of 4s or the 5s or the 6s, and so there's a little bit of freedom to shift around coming from the fact that there are more outcomes on the die than there would be outcomes, say, on flipping a coin. So the degrees of freedom kind of keeps track of that, and the degrees of freedom is you take the number of possible outcomes, in this case there would be 6 for a die, and you subtract 1. If you're looking at a coin, you would take 2, heads or tails, and you would subtract 1. So the degrees of freedom are going to be higher on a die than they are on a coin. And you want to pay attention to this. This shows up in a chart later on when we're trying to figure out whether or not we can reject the null hypothesis. Rejecting the null hypothesis is going to come down to basically checking something. We get a chi-square, and we're going to compare it to what's called chi-alpha squared, which is a critical value which we'll find on a chart. If the computed chi-square for our test is larger than or equal to the critical value on that chart, then we reject. If it's not, then we fail to reject. And that's it. This is a hypothesis test, and so we're checking whether or not our chi-square is bigger than or equal to our chi-alpha squared. So that's in a nutshell what we're going to end up doing. And so here's that table. So you will see that on the vertical axis we have degrees of freedom because it depends on the number of degrees of freedom. So in this case we're looking at the die, it's 5. And I do want to jot something down here because we're actually going to run the dice, and we're going to do 30 rolls. And what I would like to do is test whether or not this die is a fair die using a level of significance, let's say 0.025. So this level of significance is on the top at 0.025, so that's the one we're going to do, would be right there. And so we're going to use our critical value for our test. Chi-alpha squared is going to be equal to 12.833. So if our chi-square becomes larger than 12.833, we will reject. If it is smaller than that, we will fail to reject. So chi-alpha squared is equal to 12.833. In general, you will be given a level of significance, which is what you find up here. And then you also know your degrees of freedom, and then you will run down, and then that number that you get in the chart is going to be your critical value. And so we're going to actually run an example here in just a second. All right, so we're going to roll a die 36 times. And we're going to get our chi-squared. And that's equal to the sum of our observed, or our expected, minus our observed squared divided by expected. And it is possible, there are two different formulas for this. It is possible that in the formula that we just saw that this is switched. But because we're squaring it, it doesn't matter. You just have to subtract the observed from the expected or the expected from the observed, but make sure you square it and add them all up. Degrees of freedom in this case, there are 6 different things that could happen. And so our degrees of freedom is equal to 5. And that was what allowed us to, on the previous slide, look up our chi-alpha squared, because we knew that our alpha, which is equal to 0.025, we used that along with our degrees of freedom to look up our chi-alpha squared, and we already know that our chi-alpha squared is equal to 12.833. These are the two values that you need in order to look up the chi-alpha squared. If I changed the die and had a different degrees of freedom, then I had to look at a different row. Or if I changed the level of significance to say 0.05, I would have to use a different column. But we did this in the previous slide where we got the chi-alpha squared. So now I just need to know the chi squared. Now, I'm rolling 36 times. So the expected roll, the expected number of times that I'm going to roll 1, which is what E1 is, I expect to roll it 6 times. That comes out of the fact that the probability is 1 out of 6. And if I take 1 divided by 6 and then multiply that fraction times 36, I get 6. If you take the stated probabilities from the null hypothesis, in this case, our null hypothesis is that the probability that I roll 1 is 1 out of 6, the probability that I roll 2 is 1 out of 6, the probability that I roll 3 is 1 out of 6, the probability that I roll 4 is 1 out of 6, the probability that I roll 5 is 1 out of 6, and the probability that I roll 6 is 1 out of 6. The alternate hypothesis is these are not the same. Probabilities are not as stated. So from the null hypothesis, I'm given a probability, and if I multiply that by the number of times I roll, I get my expected. So my expected 2 is equal to 6, my expected 3 is equal to 6, my expected 4 4 is equal to 6. My expected 5 is equal to 6. And my expected 6 is equal to 6. Now I need my observed. Observe 1, observe 2, observe 3, observe 4, observe 5, and observe 6. So I'm going to roll this 36 times. So let me see if you can track the die. So if I roll the die here, I'm going to start, and I'm going to keep track over here on a separate sheet of paper so that we can add this up in just a second. So we just got a 1, so that's the first roll, second roll, third roll, fourth, fifth, sixth. Okay, you got to trust me that it landed on a 4, but now I've ruined your trust. 5, 2, 3, 4, 5, 6, 7, 8, 9. We're doing it 9 times. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, and 36. So let me tell you what we ended up getting for all of these. For the observed ones, we got 5. For the observed 2s, we got 5. For the observed 3s, we got 6. For the observed 4s, we got 8. For the observed 5s, we got 5. And for the observed 6s, we got 7. 5, 10, 16, 31, 36. So we got 36 there. So now we need to do our chi-square. So I'm going to just quickly, I'm going to make another column where I take the expected minus the observed. And so this column, 6 minus 5 is 1, 6 minus 5 is 1, 6 minus 6 is 0, 6 minus 6 is negative 2, 6 minus 5 is 1, 6 minus 7 is negative 1. Okay, so that's going to allow me to, I'm going to get rid of this null hypothesis and probability so that I can do the next part, which is try to find that chi-squared. Okay, so the chi-squared is equal to, so first I take the expected minus the observed squared, so it's going to be 1 squared divided by the expected, which is 6. So I did that for the 1. Now for 2, my expected minus my observed is 1, so 1 squared divided by, again, the expected, which is 6. Plus 0 squared divided by the 6. Plus negative 2 squared divided by the 6. Plus 1 squared divided by 6. Plus negative 1 squared divided by 6. Which is equal to 1/6. 1 plus 1. These all have common denominator, so I can do 1 plus 1 plus 0 plus negative 2 plus negative 2 squared is 4 plus 1 plus 1, all divided by 6, which is equal to 1, 2, 6, 7, 8. 8 divided by 6, which is equal to 1.33. So my chi-squared is 1.33. 1.33 is not larger than or equal to 12.833, which is my critical value. So therefore, I'm going to fail to reject. Fail to reject. That is my final conclusion. Now that should make sense, because look at my rolls. I rolled approximately 6 for each of those numbers. It was kind of amazing that it rolled that nicely. So why should I be able to reject the null hypothesis that the probabilities are equal to 1/6? Because that's what I basically got, was 1 out of 6 for most of those. So that's how a chi-square test works.